If you subscribe to the channel, you'll get lots of interesting videos like this one. And if you like the video, it'll really help us out. Please comment down below for any other interesting things. That also really helps us out as well. Hi, welcome to another edition of Easy Theory. So we have a very special video today in that we're going to do a first on YouTube. That's right, we're going to show that this language right here is what is called inherently ambiguous. So we actually talked about what inherently ambiguous means, but I'm going to do a quick refresher on it. So we have a language right here, and I want to make a CFG for it. So remember, we have CFG means context-free grammar. If I can spell context, that would be good too. Context-free grammar. And in creating a context-free grammar, we may have multiple ways of generating a string. So suppose that I had this grammar, and this is a famous example. Well, I can make the empty string just by going to it, or what I can do is I can have s be replaced with ss and have both of them go to epsilon. And so those are two different derivations. In fact, there are two different leftmost derivations. So here, this grammar is ambiguous because the empty string can be made in two different ways. Okay, so that's just what ambiguous means. But of course, with this language right here, which is only the empty string, I can only make the empty string with this grammar. So what I could do is I could have just used the simple grammar, which has s generating epsilon, and avoided the ss rule altogether. So just because there is a ambiguous grammar for a particular language, that doesn't mean that there is some other grammar that is unambiguous. So this grammar is unambiguous because every string that it makes can be only made in one way. So we say a language L is inherently ambiguous if every CFG for it is ambiguous. Okay, so that's actually a lot harder of a problem, because if I want to show a language is inherently ambiguous, I need to be able to convince you that every single possible grammar that you can make, there are infinitely many, are all ambiguous. Every single one. So the language that we're going to talk about here is this one right here. What is this language? It's all the strings of the form A, B's, and C's, with A's first, B's second, and C's third. And either the number of A's and B's is the same, or the number of B's and C's is the same. So the number of C's over here can be anything compared to A and B. They can in fact be the same, but the number of C's here can vary, and the number of A's here can also vary. So I'm actually not going to record this in a continuous stroke. I'm going to break it up into multiple segments because I envision this video to be very long. So I'm going to have chapters of the video in the description, and they're going to show up in the video, so make sure to click through to whatever section that you find interesting. So let's get started. Okay, so first I want to convince you that this language in fact is context-free. So in order to do that, I need to show you a context-free grammar for it. And that shouldn't be too hard. So how do we actually do that? I shouldn't zoom in. So the way to do this is to make a grammar for each of the two pieces and to do closure under union for context-free languages. So to do the first one, let's call the first one L1 and the second piece L2. So for L1, what we do is to say, well, the number of A's and B's is the same, but the number of C's can be anything. So what I do is I say, well, let's first make the grammar for a to the n, b to the n. So a, s, b, or empty. But to handle all the c's that can happen afterward, a common trick right here is to make a new variable, start variable s0, and have it make sc. And what is the c variable going to do? It's just going to spout off a whole bunch of c's. So here, the start variable s0, so this guy's the start variable, it's going to make sc. So s is going to make the a to the n, b to the n part, so the same number of a's and b's. And the c variable has nothing to do with what is generated here. So it's just going to make any number of c's that we want just by applying this rule over and over. So that makes this part right here. And then for the L2 piece, so let's put that right here. Well, it's actually almost exactly the same idea. But here we have the B's and C's need to match. So let's make a little grammar for B to the n, C to the n, BSC or empty. And then now instead of having SC, I'm going to have the A's being made before the S variable here. So I'll have S0 making a variable called AS, and the variable A is just going to make a whole bunch of A's here. So a little a, big A, or empty. So if I wanted to combine these, well, I should actually make all of the variable names disjoint. So that's exactly what I'm going to do. So I'm going to call these starting from 0, 1, 2. So these are just subscripts to determine which of the two sides of the grammar you're on. So S0 on the left side is going to stay with S0, C2. They're just names of variables. I could have called them anything. And we're not going to use this later. It's just to show you the final grammar. And then on the right side, I'm going to do this. So I'm going to have 3, 4, and 5. So the A gets the 5, the S here gets 4, 4. Oh, this shouldn't be 0 over here. This should be 1. Even I'm getting mixed up. So they're just names of variables. And I'm doing this so that it's disjoint. So that when I want to do the union of the two, so L1 union L2, what I do is I'm going to have a start variable called S, and I haven't used the variable S because I renamed the variables. So S is going to make S0 or S3 because those are the names of the start variables from before. And all I'm going to do is I'm just going to copy and paste these two grammars down here. And then I'm going to copy this one. And it is important when you're trying to do the union of two grammars that you actually make sure that the variable names are disjoint from each other. Okay, so I need to convince you, of course, that this grammar is ambiguous, because if it was unambiguous, then this video wouldn't ever be made. So I need to convince you that I can make some string in two different ways. And the pretty obvious choice here is the empty string. So I could so if I wanted to make the empty string, I could go through S to S0, which is going to make S1, C2. I should have this be double arrows. So double arrow, let's replace S1 with empty. So then we have C2, and C2 gets replaced with empty. Notice that I replaced S1 here. So I want to make sure that I'm sticking with leftmost derivations to make sure that it really is ambiguous, instead of just two different derivations. And then for the other way, we could do S going to S3, which will, of course, make A5, S4. Again, we're going to do leftmost derivations, and indeed, we do get epsilon in both cases. So now what we're going to do is we're going to start talking about the proof of showing that this language is really inherently ambiguous. Okay, so now I want to tell you about the first part of the proof, which involves something called a reduced grammar. So what is a reduced grammar? So a reduced grammar is one where every variable, let's call it A, has the following form. So it has the following form, which is that either is the case that A produces X for some X. So this is just saying that A is involved in a rule somewhere, which is totally reasonable. And the other case is that S will generate something of the form X. Actually, I'll change the variable name to be S generates Y, A, Z for some strings Y and Z. And why is this important? Well, what we want to do here is to exploit this structure in the grammar. And I can assume that such a grammar exists. So if I have any CFG, I can convert it into reduced form. Why? Well, if I have a variable that's just never used, is never on the left-hand side of any rule, then of course its usage in any rule on the right side is completely useless. So any variable that doesn't appear on the left side, I can just delete it entirely, and any rule that includes it on the right side. So it's basically just removing variables that are not used at all. But suppose that every variable is used. Well, so let's actually look at this. So if I have the start variable S and I apply a bunch of rules, and there is no way to produce something of the form Y, A, Z. So it doesn't really matter what the Y and Z are. They could be any terminals or variables. But where the variable is on the right side. So if there's no way to make this A right here, then again, its usage is completely irrelevant because S is the start variable. If there's no possible way to make this variable, even if it appears on the left-hand side of a rule, then there's no point in having this variable around. So let's just assume that we actually have all variables reachable from the start one. So I have some way of producing this variable right here. Well, then what I can do is I can actually do this. So I can, so what I can do is to add the rule. So I can add the rule S produces Y, A, Z that way. So if there's some way to produce this right-hand side right here, then what I'm going to do is I'm going to add the rule S goes to that directly. So this is a new rule that I'm going to add, and it's shortcutting our way to that right-hand side. So, yeah. But another thing that we should notice here is that we could just do this, but it's not going to preserve the unambiguousness. So if we did have an unambiguous grammar, then if we did this, then we'll have two ways of making the exact same right-hand side, which is obviously a big no-no. So what we're going to actually do is we're going to augment the definition slightly, where this right here is not a rule application, but this is a sequence. So this is a sequence of rule applications. So instead of just a single rule that we're applying a bunch of rules. Okay, so this means that A can produce something and S can eventually reach A, and that's totally reasonable, as we were saying before. If A is unreachable, then it's completely useless for the grammar, And if the variable a is unreachable, even though it's on the left-hand side of a rule, then it's also useless. So that's well and good. But the important thing here is that if we have this particular form with this augmentation right here, if we had an unambiguous grammar, then if we remove all the variables a where it doesn't appear on, if it doesn't appear on the left side, I delete those rules that have a, and I delete a variable a if it's unreachable, I preserve the unambiguousness. Okay, because if I'm deleting rules, I never will make it ambiguous. Remember, ambiguous has two different ways of making a string. If I have only one way of making it, and I delete the one way of making it, I can't have two different ways of making that string. So this tells us right here that if G is an unambiguous grammar, CFG, then there exists an unambiguous reduced, spelling would be good too, reduced CFG for the same language. Because all we're doing is we are deleting useless variables. Okay, so that is the first definition that we'll actually need. We're going to look at another definition next. Okay, so another definition that we'll need is something called almost looping. So what does almost looping mean? So a CFG is almost looping if we have three different properties. So if one, actually I should give it a name, so I'm going to call it G. So if G is reduced, which is, we can assume that the grammar is reduced because we can turn any grammar into a reduced one. And second, then what we're going to define is a set. So before I get to the second and third one, we're going to define a particular set. So we're going to call it loop vars of G. And what it is all of the variables that have themselves on the right side. So it's all of the variables A in the set of variables, such that A, which produces XAY, is, I shouldn't use a double arrow for this. X going to XAY is a rule in that grammar G. And why is this useful? Because the X and Y can be anything, but the variable A is something that we're going to be exploiting later in the proof. So, so this is the set of all the variables in the grammar that have themselves on the right-hand side of some rule. So if I have, for example, B goes to epsilon, and that being the only rule that B is involved in on the left side, then B is not in loop vars of G because B is not on the right-hand side here. Okay, so almost looping, well, what does that mean about the loop vars variable? So all variables other than the start one are in loop vars of G. I haven't proven that we can always have such a grammar like this, but we will prove this. So in the third one, then either it's the case that S is in loop vars G, or it's the case that S appears only once in any derivation. Okay, so it either has itself on the right hand side, or it only will appear once at the very start of the derivation. Okay, so next what we're going to do is we're going to prove that we can convert any CFG into an almost looping one. And in the process, any unambiguous grammar can be converted into an almost looping unambiguous grammar. So the almost looping property can be preserved even for unambiguous grammars. Okay, so we're going to prove that any unambiguous grammar that can be converted into an unambiguous grammar that is also almost looping. So that's what we're going to prove right here. So lemma, any unambiguous, I'm going to shorten it to that, CFG can be converted into an unambiguous, almost looping CFG. And of course, it has to have the exact same language. Okay, so how are we going to actually prove this? So at a high level, what it does is the way that the proof goes is based on induction. So induction, what that means is that we're going to have a base case and then an inductive case. So the base case here is based on the number of variables. So the base case right here is that S is the only start variable. So not the only start variable, the only variable total. And why is this an almost looping grammar? Well, it's reduced because there's no other variable like this. All variables other than S, there aren't any. And it's either in loop vars or it appears only once, in which case it would only have terminals on the right-hand side because S is the only variable. So if it had a variable on the right-hand side, it would satisfy this first one, and if it didn't, it would satisfy this one. So that's pretty clear. So what about the inductive case? So inductive case. So how does this work? Let's say that the variables are called A1 through what's my notation? AK. And let's let, we're going to let A sub k plus 1, we're going to have that be the variable S. So S is going to be k plus 1, and we have k other variables. The case right here is when k was 0, and so there would only be one variable, of course. So we're assuming that k is at least 1, which means there are at least 2 variables, of course. So let's see. So what we're going to do is the following. So we're going to look at a particular variable. So let's look at variable a sub I. Well then, at this point, it either is in the loop variables or it isn't. So, and actually what we're doing here is for all I between 1 and k. So this isn't just like we're picking one variable, we're going to look at every single one of them, but this is just what it looks like from a single variable's perspective. So we're going to look at a single variable AI right here. So then what are we going to do with it? Well, it either is in the loop variables or it isn't. So, so the case 1, so to speak, is that AI is in the loop variables of G. Well then, in this case, we are already done because we require that every single variable other than S be in the loop variable set. And I'm looping over the ones that are not S. So this one better be in the loop variables. So if it is, great, we're already done. But the other case is when it's not there. So case 2. So AI is not in loop vars of G. So what do we actually do in this case? So what we can notice from this right here is that AI has a bunch of rules, and itself, AI, is not on the right-hand side because we are assuming that it's not in the loop variable set. So so all of its rules are going to be like x1 or x2, or let's just say xr. So there are r rules, let's say. And what we can determine here is that none of these right here, so none of the xi right here, have AI. I should actually change this to xj. Actually, I'm going to change it to xm. Well, one of the hard things about giving proofs is that you run out of variable names quickly. But so this is just a restatement of what this says. So AI is not in the loop var set, so we're going to look at its right-hand side. And it has it may have some variables, but it definitely does not have AI on the right-hand side. And so therefore it's not a looping variable. So what do we actually do? So what we're going to do is something that's actually pretty clever. So we're going to look at all rules, every single one, aj. So this is a different variable where it produces some string either of terminals or variables or both. So we're going to look at all rules that look like this. And so this right here, this omega, it looks like a W, but it's omega. So this can have variables and terminals or a mix. It could have any set. So in fact, AI, the variable we're interested in, could very well be over on this right-hand side. We don't know for sure. But we want to do the following. So what we're going to do is we're going to replace this. So replace this rule right there with some number of rules. And what is this? We're going to have r to the m rules. And where does the m come from? So notice that the r came from the number of rules that AI has. And what does the m come from? So m right here is the number of occurrences of AI, the variable we're interested in, not aj, AI, in that right-hand side omega. So AI, if it occurs 0 times, then we're going to replace this with one rule. So we're going to place one rule with one rule, and in fact it'll be the same rule, so nothing will change. But if AI does appear over here, we're going to actually replace it with a whole bunch of rules. And in fact, this is, if you saw the Chomsky normal form video, this is almost identical to one of the steps there. So what are we going to do? So what is it going to look like? It's going to look like aj, we're going to have omega 1 or omega 2 or omega r to the m. So the number of right-hand sides here is indeed r to the m. So what are we going to do? So what we're going to do in each of these right here is going to correspond to some number of deletions of the I variable. But what we're going to do is we're going to replace the AI variable with the right-hand sides originally. So let's just say that we had aj goes to y, a, I, z. Then what we're going to do is we're going to replace this with aj going to y, x, x1, z, because remember, x1 through xr are the right-hand sides of AI, or y x to z, or y x to xr z. Okay, so effectively, we're making this variable completely useless, right? Sorry, AI useless. We're making AI useless because we're replacing its occurrences with its right-hand sides. And if, let's just say that there are m occurrences of each AI, well, if there are right-hand sides for the AI variable, and I have m places to fix in them, in fact, so therefore we will get r to the m possible rules. So here we are replacing AI with its right-hand sides in all possible ways. Okay, and you can actually see from this, because all we're doing is replacing each possible choice of a rule from AJ and then one rule from AI. We're replacing all of each of those individual choices with one rule. So adding rules might change the ambiguity of the grammar, but what we're doing is we're replacing each of the occurrences with one rule. So we're replacing effectively one choice of rule with one rule. And so therefore, we can actually assume then that the grammar is in fact unambiguous as a result. So now what we're going to do is we're going to look at the language that we're interested in and notice some important properties of it with regard to it being almost looping in a hypothetical unambiguous grammar for it. Hi, so now we're going to prove the main technical lemma of the entire proof, but one thing that I should mention before we do is that the y's and the z's here, we can actually assume to be completely sets of terminals. So we can assume that these are entirely terminals. And in fact, the proof will go exactly the same if we assume this. But it's actually important that I mention this now before we get into the lemma, because it heavily uses the fact that if you have an almost looping grammar, then the stuff on both sides of the variable, where it has the same on both sides, those need to be terminals entirely. But you can assume that they're entirely terminals. All right, so here's the lemma that we're going to prove here. So let's let G be an almost looping grammar. And we're going to have it be such that its language is the one that we actually want to observe. A to the I, B to the I, C to the J, where I and J are at least one. Union, the other language, is where we have the number of B's and C's being the same. So we have the J exponent being the same on the A's and B's at the start, and B's and C's on the second piece. Okay, so what are we going to prove here? So what we have is that every non-start variable, let's call it A, is exactly one of the three types. And I'm going to define what those types could be. So type 1. So what is type 1? So there exists an integer m, which could depend on the variable, of course, and strings x and y, such that so what are we going to have here? We're going to have A producing xay, and what we have here is that either xy is in A star. Yeah, so I should actually say it's not exactly this. It's equal to A to the m. I didn't want to say A star there because m is at least 1. So x and y, in some sense, there's at least one A, and they're entirely full of A's. So there's no B's or C's in this. So it's either the case that we have this, or xy is C to the m. So it's entirely full of A's and at least one of them, or entirely full of C's and at least one of them. So that's type 1. Type 2. So type 2, we have that there exists an integer n sub a, which is also at least 1, such that the variable a, I'll change colors again, such that a goes to a, so this is actually produces, and actually it should be produces over here too. So it's not a single rule, it's just like it can generate this in some number of rules. So for this one, it says in some number of rules we can apply, we have a to the n sub a, then a, and then b to the n sub a. Okay, so this is just saying that it will have basically just produce a to the n, b to the n, or at least have a way of making strings of the form a to the n, b to the n. Or it could be of type 3, which is there exists an integer n sub a, such that we have a very similar type right here, but now we're doing b's and c's. So b to the some number, then the variable a, then c to the exact same number. So it's either that it makes the a and b being the same part, or the b's and c's being the same part. And then additionally, so we're going to have, so every single non-start variable must be one of these 3 types, and it can't be any other, it can't be 2 types, and it can't be something else. But we're going to have something else that has occurred. So additionally, we're going to have that the start variable appears exactly once in every derivation. In every derivation. Which is kind of surprising, because we had that s could appear on the right-hand side here, but in fact we can actually assume that s will have exactly one appearance in every derivation. It can never appear twice, so it can never be on the right-hand side of any rule in some sense. So, and then one more additionally, believe it or not. So one more additionally, we have that there exists an integer, we're going to call it L here, such that every string X that can be made by the grammar, so any string that it can make at all, whose derivation only involves s. So it only involves the variable s right here, and variables of type 1. So remember type 1 above. So if it only has variables of those types, contains fewer or at least strictly less than L B's. Okay, so this one is kind of a mouthful, but so let's just assume because we have three different types of rules of variables right here, and any of the variables could fall into one of those three buckets if it's not the start variable. So if we happen to have a string that involves the start variable as well, it has to, and variables of type 1, so no variables of types 2 or 3, then what we have here, then there's an integer, a fixed integer, such that those strings contain fewer than L b's. So in some sense, we can't get a string with too many b's if it avoids variables of types 2 and 3. Okay, so what we're going to actually do in the next segment is actually prove this monstrously long lemma statement, but it actually is pretty straightforward in how it's actually proved. Okay, so let's actually try to start proving this lemma right here. So the one that we're going to prove first is that every non-start variable is exactly one of these three types. So what we're actually going to do is we're going to proceed in stages. We're going to show that it's at least one of the three types, and then we're going to show that it can't be two types simultaneously. And then after that, what we're going to do is we're going to prove these two down here. So what we have here is that every non-start variable, let's call it A, is at least one of the three types. So what do we know? So what we know is that we have an almost looping grammar. So that means that A is in one of those loop var, it is in the loop var set. So that means that we have that A is going to produce in 0 or more of rules. It's going to produce a Y, A, Z, where Y and Z are, I'm actually going to switch terminology to be X and Y, because that's what I have in my notes. Okay, so what we have here is that we have something that like this. So one thing we're going to show is that X and Y cannot have a mix of terminals. And that's actually kind of easy to see, because what we can do is we can just apply this over and over. So then we say, okay, well, A is going to produce X, A, Y, and then we'll apply those same rules again to get X, X, A, Y, Y. So suppose that X, for example, has A's and B's in it. Then that means that this X also has A's and B's in it, which means that we'll have A's, then B's, followed by A's. But remember that the language is A's, B's, and C's in that order. So it can't be the case that they have a mix of terminals. So what we can notice here is that X and Y must be in either all A's or all B's or all C's. So it can't be that there's a mix of A's and B's anywhere. So there's some things that we can notice, like because Y occurs later than X, then if X has C's in it, then Y also has C's in it. If Y has A's in it, then X has only A's in it. If X has B's, then Y is either B's or C's. So it's not like X can have B's and then Y has A's, because A's were earlier in the string that we're trying to make. So here's one thing that we're going to show. So we're going to show that if we take this, so we're going to show three things. We're going to show that X, Y, the string together, cannot be only B's. Okay, so this notation, if you haven't seen it before, is at least one B. Okay, B star with 0 or more occurrences, B plus is 1 or more. So it's not the case that X and Y have only B's. So it's either, yeah, so they both can't contain B's simultaneously. So then the other thing we'll show is if X only has A's, then Y only has A's or B's. So it can't have C's at all. And then the third thing we'll show is actually very similar. So if X only has B's, then Y only has B's or C's. So this one's actually pretty clear. This one I don't need to explain because Y is later in the string. So actually for this one, it's actually not so trivial. So, but what we'll try to do is we'll look at this one and see where we get. So what we have here is that because we have a reduced grammar, we should be able to derive something like this. So the start variable is going to have some number of rule applications to derive something of the form, let's call it P, A, let's call it, I don't want to mess up my notation. Let's call it alpha A beta. And let's say that that is going to eventually produce A to the R, S, sorry, B to the S, C to the T, such that either R is equal to S or S is equal to T. Okay, because by definition, that's what the language is. So if we get a string like this, either the number of A's and B's is the same, or the number of B's and C's is the same, which is what this is. So let's just assume that in the derivation, we get the variable A at some point. And we need to be able to, because the grammar is reduced. So we should be able to get this variable somewhere. And now what we know is because the grammar is almost looping, what we can get is in between here, we should, or not in between, we should be able to derive from this alpha and then just an application of the almost looping property, which is that A can produce X, A, Y. So we have X, A, Y, beta. And notice that we can apply these, apply this step right here over and over as many times as we want, because we still have the variable A right here. So let's say that we apply this Q times for some integer Q, okay? So what we're gonna get is that we're gonna get X Q times and Y Q times, okay? So let's see. So what are we gonna get here? So if X and Y only have B's, then let's just say that X, Y is equal to B to the M for some integer M. Well, then what we can get from this is that, actually let me change it to yellow. So then this tells us that alpha X to the Q, A, Y to the Q beta, the thing that we were able to get, is in fact the same thing, or at least if we apply the same rules that we got from here to get to here, we're going to get A to the R, which is because we never got any more A's because X and Y only have B's in them. Then what we're going to get is B to the S, because we had S B's from applying the same rules here. Then what we're going to get is plus Q times M, because we have Q applications of getting M B's every single time. And then we still have the T C's at the end. And what we will get is, if I make Q big enough, then the number of B's is going to be larger than the number of A's and C's. So once Q is large enough, then we have more B's. I should make that look better. More B's than A's or C's. And that is not in the language. Why? because either the number of A's and B's is the same or the number of B's and C's is the same. Okay, so if we have more B's than A's or C's, then obviously it's not in the language anymore. So now what we get, so now let's actually look at the other property right here. So let's suppose that X only has A's and Y only has C's. Because, of course, it can't be a mix. So let's say that X only has A's, and this is not true, that Y has only C's in it. So let's just assume that that's the case. So let's say that if X is equal to A to the M for some M, and Y is equal to C to the N for another integer N, then what we can get just by applying the same argument is that the string A to the R plus QM, if we apply that application Q times just like we did before, then B to the S, the number of B's never changed because the X's and Y's don't have B's in them. And what we're going to get is C to the T, because we got TC's from the previous set of rules, plus Q times N must be in the language because of the grammar, which means because we can actually generate that string. But this is impossible because if I make Q big enough, then this will both of these numbers, this one and this one, will be both bigger than S right here. So once again Q is large enough, then the number of A's and C's are going to be much, much bigger than the number of B's. And so therefore it can't be equal. Okay, so what do we get here? And so we got that 1 was true, 2 is true, because we assumed that it wasn't. And this one is pretty obviously true because we'll get a string that's not in the language if the Y part has A's in them, because the A's need to be before the B's instead of after. So in fact, all of the variables, so that means that, what do we have here? So what we have is that there must be variables of this type. Okay, so how does that actually help us here? So what we notice is that, so what does that actually tell us? Okay, yeah, so that's what we wanted to prove right here. We wanted to prove these three statements right here. I had lost my train of thought. All right, so what do we want to do here? So now we want to show that it's one of the three types. So let's let X be in either only A's or only B's or only C's. Okay, so then what we have here is if X is only B, so let's say B to the M here, then what we have is that, actually no, sorry, it's A's. I got this mixed up. If it's only A's, then what we have is that the variable that we're looking at right here, the variable A, must be of this right here. Must be this. And actually from that, therefore, it must be one of these two types. Okay, so and that's actually not hard to see. Put into the comments if you want to see this done more in depth. So it must be one of those two types. So yeah, so then that means that A, the variable A that we're interested in, is of type 1 or 2. If X is just only B's, not star, is M, then by the same logic, what you can get is that A is of type 3. Okay, and if X is only C's, then what we get, you can do the same logic, is that A is of type 1. And in the other case, it could be that x is in fact equal to the empty string, because in these cases it involves at least one of the a's, b's, and c's, but it could be that x is empty, because there was nothing in what we did before that said that the x and y had to be non-empty. It could be that one of them is empty. It can't be but both of them is empty, but one of them could be empty. So if x is empty, then y is obviously non-empty. So then what we can actually derive here, based on what we did and try to actually think about why this is, that y can't be in b plus. So it can't be only b's, and that implies that a is of type 1. Okay, so in all possible cases of what x could be, the variable a was one of those 3 types, which is exactly what we wanted to prove. So now what we're going to do next is we're going to show that every variable can belong to only one of those 3 types and can't belong to 2 of them simultaneously, which it appears that this one and this one, actually these two, so this one right here doesn't really clash with the other ones, but it turns out that we can show that every variable can belong to exactly one of the 3 types and won't belong to 2 of them simultaneously. So that's what we're going to prove next. Okay, so now what we're going to do is we're going to show that every variable belongs to exactly one of the 3 types that we talked about before. So every, I guess non-start, I should say, a variable is exactly one of 3 types. Okay, so how are we going to actually prove this? So let's say that this one's actually done by contradiction. So suppose that the variable a that we're interested in is of type 1 and 2 simultaneously. So then what we notice is that by that logic, this tells us that a, because we're in an almost looping grammar, we have that a will generate something of the form x, a, y, where x and y are only a's or only c's. It can't be only b's because we proved that that can't be the case before. So it's only a's or only b's. So then what we can actually also deduce is that a will generate a to the n, a, b to the n for some n. So n is at least 1 here. So remember that the variable could actually generate a's and b's in the same number on both sides. But what we can actually see here is if we look at this, we see, okay, well, a will generate a to the n, a, b to the n, but then we apply this one right here some number of times. So what we are going to get here is that we have a to the n, x, a, y, b to the n. Oops, I got that. Yeah, that's right. And what we'll see here is that, well, the x and y are of the same character. So if it's the case that they only have c's, then that's a contradiction. That's a contradiction because that would imply that we have a's followed by c's, then b's are later, which is in the wrong order. So the case of only c's, that can't work. So now let's look at the case of where we have a's. So let's say that we have, let's say that x is a to the m1 and y is a to the m2. So that's the number of a's in each one. So this tells us that so what we were able to derive is a to the n plus m1, a to the m2, b to the n. Okay? So what do we actually get here? So what we're going to get is, well, if M2 is 0, so if M2 is 0, then we're going to get a contradiction based on what we did before, because we got more A's over here than we have B's. So that can't be the case. So yeah, so what we get is so a contradiction because more A's than B's by effectively the same set of rules, because we can so it'll be able to derive a different number of A's and B's, which was a contradiction for the type 2 variable right here. So then if we get exactly if we look at the other case, if M2 is not 0, we actually will still get a contradiction. And I want you to actually think about why that's the case. So put into the comments what you think. How do we get a contradiction here? So that's actually a proof that we have a variable can't belong to types 1 and 2 simultaneously. So if we have instead, so if A is of type 1 and 3, if you do a very similar proof, then you can actually show that that's the case too. But the other case is if A is of type 2 and 3, then what do we should notice something here. So what we notice is that A can generate A to the n, A, B to the n. But it can also generate A goes to B to the m, let's say A, C to the m, because this is of type 2, type 3. So what do we notice here is that we just apply these twice. So if we do this first one and then apply what we did here to this variable A, this set of rules, then what we'll get is A to the n, B to the m, A, C to the m, B to the n. But notice that we have C's occurring before B's. And so therefore, it can't be type 2 and type 3 simultaneously. Okay, so that was quite a lot. And what we're going to do is finish up the lemma with the last 2 pieces in the next part. Okay, so we're going to finish up the lemma and prove the last 2 pieces. So the first of the last 2 pieces is that the start variable s cannot appear twice in any derivation. So why is that the case? So let's suppose not. Let's suppose that s can actually make something of the form xsy, and of course if x and y are both empty, then clearly the s makes s, and that doesn't tell us anything. So we're going to assume that x and y together are not empty. One of them could be empty, but they both can't be empty. So what we can actually see from what we did above is that this implies that s is of type 1, 2, or 3. Remember, the lemma said that every non-start variable was one of those 3 types. But it turns out that the start variable from this is one of those 3 types, but what we're going to prove here is that this is a contradiction. So why is it a contradiction? So let's suppose that this is actually the case right here. So we have that s is going to make xsy, and let's suppose that right here we have x, y only have a's. But that's clearly not going to work, because if we have a's on the front and the end, because there's nothing that this s got replaced with, that means that I'm going to generate a string that starts and ends with a's, which is impossible. Okay, and the same is true if you have b's, same is true if you have c's. Okay, so that's actually a pretty quick proof that it can't be of type 1. Okay, so what do we actually get here? So in fact, the other two cases are actually kind of similar. So what we can actually do here is suppose that we can actually do the following. So let's say that we can make S generating a to the n sub s, s, b to the n. So this is case 2. So the number of a's and b's is the same here. But then that means that what we can actually do here is, so you may think, okay, this is fine because the number of c's could be in fact 0. But what we can actually notice here is that the string A, B, C, C is in the language because the number of A's and B's is the same. So this should be able to make then A to the n sub s, A, B, C, C, B with ns there. And clearly that's not in the language at all. And in fact, type 3 can be handled almost identically to this because it's very similar. Okay, so that tells us that the start variable can only appear once in any derivation. It can't appear twice. So what do we actually what can we actually prove here? So what is the last one? After all this, my goodness. So there exists an integer L such that every string whose derivation only involves s and variables of type 1 contains fewer than lb's. So let's say that we are doing that part right here. So let's just say that suppose not. That means that L does not exist. That upper limit on the number of b's in those strings that only involve type 1 variables. Okay, so they only involve type 1 variables. They don't involve type 2 or 3. So how do we actually use this to our benefit? So what we must be able to generate a lot of b's from this, because if the upper limit doesn't exist, then I can just make a lot of b's without ever stopping. So what can we actually do here? Then that means that for some, maybe not all, but at least some variable, let's call it A, we have that A will generate x, a, y, where x and y have at least one occurrence of a b. Because if they didn't, then there are only finitely many rules, and so I can only get a finite number of b's as a result. So there must be some kind of cycle that happens here. But this type of variable must be either of type 2 or 3, because that's how we defined it here. And so that's a contradiction, because we assume that L doesn't exist, which means that if we involve type 1 variables, then that tells us we must involve a type 2 variable, which is a contradiction. Okay, so that actually concludes the proof of the really technical lemma. And then now all that we need to do is to wrap things up in the major result in showing that this language, finally, is inherently ambiguous. Okay, so now we're finally able to wrap things up and to show that this language is inherently ambiguous. So let's actually make sure we get this correct and write theorem here and eventually hopefully declare victory. So the theorem is that the language, let's write it here just so that we remember, a to the I, b to the I, c to the j, where I and j are at least 1, union a to the I, b to the j, c to the j, where I and j are at least 1. And so this language is inherently ambiguous. Okay, so let's actually get through this. Although that doesn't sound right, but I want to actually get to show you the beauty and how we wrap things up. So how do we actually do this? Well, we started off by showing that we can convert any unambiguous grammar into an almost looping and reduced one. So let's write proof. So let's let G be an almost looping reduced CFG for L. And what we're going to show here is that it must be unambiguous. Sorry, it must be ambiguous. So let's suppose here that it was unambiguous. So suppose G is unambiguous. Okay, so what are we going to actually do here? So all that really big technical lemma that we did applies here because we're dealing with an unambiguous, almost looping, reduced grammar for this language, which is what the lemma dealt with. So if you remember, we had those type 1, 2, and 3 variables, which had the n sub a constant on there. So especially for type 2 and 3, we had a going to a to the n sub a, capital A, b to the n sub a. So something like this. So what we're going to do here is actually something that's kind of strange, but it actually turns out to be really useful. So what we're going to do is we're going to let k be the product over all variables a of that constant n sub a. So all of those n sub a's, we're going to multiply all of them together. So if it was 2, 3, and 5, for example, we would get 30. We're just multiplying them together. So we can't actually do this in general because we need to assume that, first of all, where the variable must be of type 2 or 3. If it was a type 1, this number doesn't exist. So we need to make the assumption that A is of type 2 or 3. Because if it's type 1, then this number isn't defined. So for type 2 or 3, it is defined. So that's fine. And what we want to do is we're going to pick any integer p divisible by k. Divisible by k. Okay. And in fact, it must be bigger than L, which is the number that we dealt with earlier. So if you remember up here, God, way up here, this integer L right here, then it turns out that we need to be at least that integer due to dealing with trivial cases and whatnot. But pick any integer that is divisible by k, at least this number. We could pick k itself, but just pick any one that you wish. So let's we're going to let z be the string a to the p, b to the p, c to the p. C to the 2p, sorry. Well, clearly this string is in the language because the number of a's and b's is the same. So this is in the language L for sure. So what we notice here, let's look at how we actually derive this string. So we have s right here. Then let's suppose that we had something of the form alpha a beta, and that generates a to the p. Well, actually, it's just the string z. Okay, so let's suppose that we had something like this. And what we can assume, we can show that A cannot be of type 3. Okay, so let's suppose that it was of type 3. Well, then that means that we're going to get equal number of B's and C's on both sides. So, yeah, so what does this actually show? This says that S is going to make alpha A beta, which is going to make alpha B to the P A C to the P beta. Okay, but what would that actually tell us here? Well, this string right here, from here, we're going to get PAs, PBs, and 2 PCs. So what we're going to get is A to the P, B to the 2P, C to the 3P. But that can't be in the language, obviously, because the number of A's and B's is not the same, number of B's and C's is not the same. Okay? So let's see. So let's actually think about this more. So it turns out that in the derivation right here, in the derivation we cannot only use type 1, not that one, this one, variables. Because, in fact, what we'll get is that we won't get enough B's as a result, and I want you to think about why that's the case. So let's let, so that means that A must be of type 2. A must be of type 2. Type 2. Okay, so then that means that A must be able to generate A to the P, A, B to the P. Because that's what type 2 says. Okay, so then what do we get here? So we have S will generate here alpha A beta, which is going to make alpha A to the P, A, B to the P, just by substituting this part right here, beta right here. And notice that we're going to add PAs, we're going to add PBs, and 2 PCs, because that's what we got up here. So we're going to add PAs, we're going to add PBs, and 2 PCs. So the final string we'll get here is A to the 2P, we added P more. We're going to get P more Bs, and 2 PCs, which is clearly an L, obviously. So what are we going to actually get here? So yeah, so what we can actually see here is in deriving that final string, A to the 2P, B to the 2P, C to the 2P, no variables of type 3 were used. And at least one, although maybe more, type 2 ones were used. Type 2 vars were used. Okay, so nothing of type 3 was used, but at least one of type 2 was actually used. So yeah, so what are we going to actually get here? So let's actually consider this one instead. So let's consider Z prime to be A to the 2P, B to the P, C to the P. Well, that's clearly also an L because the number of B's and C's is the same. So what we can actually derive using the exact same logic is that in deriving A to the 2P, B to the 2P, C to the 2P, because from here we can use the same logic to actually end up at the exact same string. In deriving this, no vars of type 2 in this case were used, but at least one type 3 var was used. Okay, so So I want you to actually think about this in being able to get through this last bit and showing that we still get the exact same string in both cases. So because we got the exact same string in both cases right here and here, then that means that we got the exact same string in two different ways. And we know they're different. It's not that like they're just two different versions of the same derivation. We know that they're different because in the first one, we only use type 2 variables, and in the second case, we only use type 3 variables. And we saw that no variable can belong to type 2 and type 3 simultaneously. Isn't that really cool? It's a lot of work to be able to show one string would be able to be generated in multiple ways, but that's enough to be able to show that this grammar is ambiguous. And we started off by showing or assuming that it was unambiguous, and then therefore that's a contradiction, and then therefore the language is inherently ambiguous. All right, that was pretty fun. So leave your thoughts about this language in the description. I would be really interested to know other proofs of inherently ambiguous context-free languages, because being able to prove them is actually very, very difficult. If there's a simpler proof of this very same language, I would love to know it. If you want to support the channel, you can do so by liking the video and subscribing to the channel. There are many other links in the video description that you can help support the channel, such as our Patreon or our Discord. Commenting down below also really helps. Thank you for sticking around to the end, and as always, I'll see you next time.